Hello everyone, my talk is titled, Do You Feel What I Hear? Enabling Autonomous IoT Device Pairing Using Different Sensor Types. My name is Jun Han and my co-authors are Albert Chung, Manal Sinha, Madhu Harishankar, Shijia Pan, Hae-young No, Pei Zhang, and Patrick Tag, and we're from Carnegie Mellon University. So securing a smart home IoT network becomes a necessity as introducing more IoT devices comes at a cost of potential privacy leakage, as shown in these recent articles. This is because many of the IoT devices are equipped with sensors that monitor users' daily activities at home, and therefore it has a potentially privacy-sensitive information. Hence, it is very important that these devices have an adequate method of establishing trust, also shown by the previous speaker, in other words, a secure pairing. But as we see also from the previous speaker's presentations, secure pairing has to be protected against man-in-the-middle attacks. In order to protect against such attacks, unfortunately, many of the existing solutions actually required an active user involvement, such as typing in password, and we're all very familiar with such process. However, human-in-the-loop solutions such as these actually is still a long-standing problem, causing various usability concerns and as well as security concerns. Well, I have a bad news for you today. As these devices are increasing with the advent of the IoT, especially in a smart home, there are various challenges. Specifically, I want to highlight the two main challenges. First, there are too many smart home devices today, and there's already tens of devices today, but it's going to increase to hundreds of devices within the next few years. So it's going to be very impractical to assume that a human user would be typing in passwords around the house. Actually, more seriously, there's not even an adequate user interface on these devices. So imagine your motion detector in a smart home. Where are you going to type in your password? Because there's no keyboard or displays. So these problems motivated researchers to eliminate the active human involvement in these protocols and initiated what is called the context-based pairing. So context-based pairing takes as input common observations of the physical context. As shown in this figure, there are two microphones inside this house, and therefore these microphones actually observe common random activities such as human walking by or doors opening and closing, and then use those common observations as sources of entropy to be fed into a cryptographic protocol to establish a shared key. But the problem is that these context-based pairing is limited to the same sensor types across these devices. In other words, homogeneous sensing modality as shown in this diagram. So in the rest of this talk, I'd like to try to answer the following motivating question. How do we actually apply the existing context-based pairing to allow devices that do not have the same sensor types as shown in this figure? So to answer that question, we want to provide what we call the cross-modal context-based pairing. And in this figure alone, you already have 4 different types of sensors. And we wanted to ask, what can we do to provide this cross-modal context-based pairing? And specifically, we asked the question, what is the commonality across these different devices? In other words, what is the invariant property across these sensors? And it turns out that timing information is the invariant property across these different sensors. So let's take a moment to imagine the scenario where if you have a microphone such as the Amazon Echo in your home, and let's say a power meter that measures the voltages connected to, let's say, a coffee machine. So when the coffee machine starts grinding the beans, the microphone hears the sound of the beans grinding. At the same time, the power meter actually measures the voltage spikes. So using the commonality, we actually, in the paper, we defined this as a phenomenon called a numerically different yet contextually similar phenomenon. So let me give you an analogy. If I put a blindfolded person who cannot see, and a person with a headphone, so she cannot hear, both into the same room and open and close the door of that room, both persons can actually come to an agreement at the end to find that they've actually perceived the same event because the blindfolded person can hear the event, and at the same time, the person who cannot hear can actually see the event at the same time. So to provide an intuitive example, imagine a smart home equipped with these three sensors: geophone on the top, which is a vibration sensor, a microphone, and again, a power meter, again, hooked up to a coffee machine. The raw signals on the right represent the resulting time series signals of each sensor due to the following exemplary scenario. So in this home, there are two residents, Bob and Charlie, who are housemates. And Bob knocks on his roommate Charlie's door to invite him for a cup of coffee in the living room. And then Charlie opens the door and joins Bob in the living room. They make 2 cups of coffee, and Charlie goes back to his room and shuts his door. So in this scenario, you can already see from the first 2 raw data that the geophone and the microphone have perceived knocking, door opening, and far to the right, door closing events almost roughly at the same time. And also, similarly, the microphone and the power meter have perceived the coffee machine, 2 cups of coffee, coffee grinding at the same, almost roughly at the same time. So again, the takeaway message from this example is that these devices tend to perceive common events even though numerical results are different at the same time. So with this intuition, I'd like to propose our solution called Percepio, which is perception in Latin. And the goal, of course, is to provide a cross-modal pairing that enables devices to generate a shared cryptographic key at the end by proving that these devices are co-located inside a house, and they observe similar events over time. And we want to enable these devices to consistently observe similar events over time, or same events over time, gradually building on a high confidence key, which we call in our paper key strengthening process. And the attacker model is that the attacker locates his or her device just outside of the house, but still within the wireless communication range. And that's because we have a notion of a physical security. We have an assumption of this notion of physical security where the homeowner would not allow an untrusted person to sneak into his or her device inside the house. And the attacker tries, therefore, to locate his or her device outside of the house and to launch what we call the shamming attack in our paper, which is nothing but the attacker trying to fool the legitimate devices inside the house into believing that the attacker's device is also inside. But as we'll see from the evaluations, that it turns out to be very difficult to do this for the attacker because of such low fidelity of information that the attacker's devices can perceive from the outside. Now, taking that information, I'd like to present our high-level overview of our protocol. So here again, we have the microphone and the power meter set up, and we're trying to pair these 2 devices. And initially, of course, we have this numerically unequal raw signal, and then we want to convert or translate this numerically unequal signal into a similar fingerprint bits. And then afterwards, ultimately, we want to get to the final numerically equal symmetric key, and we do that by feeding in the similar fingerprint or the fingerprint bits into a key agreement protocol, which we use fuzzy commitment schemes, which is using error correction codes. And the main contribution of our work is to translate the unequal raw signal into the similar fingerprint bits. And I'd like to very briefly discuss how we do that, in other words, fingerprint extraction. And so first, each device, in this case the microphone, clusters the signal according to the event type. So in this case, the star represents the knock cluster. The triangle represents the door opening and closing cluster. And then the diamond represents the coffee machine cluster. And then the devices actually compute the starting point intervals of different events within the same cluster to be encoded as fingerprint bits for each cluster. So now we have a fingerprint bit for the triangle cluster, and then we also have the fingerprint bit for the diamond cluster. the use of the starting point interval is very important because it allows the perceptio to be robust against time synchronization problems across devices. Additionally, use of the clustering is also very powerful because the devices then do not need to know what each cluster corresponds to in terms of the event types. Hence, perceptio does not require any training phase. And similar thing happens with the power meter. Here, we only have a single fingerprint because there's only one event. And perceptio requires the devices to repeat the protocol multiple times. Upon a successful finish of a single iteration of the protocol, the devices would increment the confidence score. As these iterations keep repeating, it gradually builds the confidence over time. And once a confidence score threshold is reached, the devices have now proved to each other that they are indeed co-located. And so I'd like to now move on to the evaluation. And the goal of our evaluation, of course, is to demonstrate the robustness of perceptio protocol even during the attacker presence. And we'd like to evaluate things like how likely the devices inside are to establish keys across each other. In other words, how similar their fingerprints are. And also, we would like to evaluate how dissimilar the fingerprints are across devices or between devices inside and outside. And we've performed a comprehensive evaluation across various parameters such as event, sensor, and floor types, and also distance between the sensor and the event sources, the background noise, and the effective pairing time. So I'd like to present a evaluation setup. And here, what we've done is we've actually rented out an entire squash court. But on our campus, the squash court is actually like a single building just with a squash court inside. So it sort of mimics the single detached housing, which is the reason why we chose that spot. And we've filled up that squash court with various sensors that are representative sensors of the commodity smart home devices, such as the power meter, hooked up to a coffee machine. So we brought our normal Nespresso capsule-based coffee machine into the squash court. We've also brought microphone. We've also had a accelerometer hooked up on a wall. And we've also had geophone, which is a vibration sensor on the floor. And we've had a PIR, normal motion detector. And similarly, we also had this exact same types of sensors just outside of the squash court to represent the attacker devices, but we've also added additional attacker devices to grant more information, which I'll explain in a bit. And inside the squash court, we've invited multiple participants to perform daily activities such as walking, making coffee, and knocking. So specifically for the attackers, now this figure illustrates the attacker devices that are located in the outskirts wall of the squash court. And you can see that in addition to the 5 normal sensors, we've granted 2 additional higher quality sensors to grant more capabilities for the attacker. Specifically, we have the higher quality microphone, which is 100 times more expensive than the normal microphone, and the higher quality accelerometer, which is 10 times more expensive than the normal microphone. So I'd like to present the summary of the evaluations. So we found that from our evaluations that sensors inside the building detect events with much higher accuracy than the outside. And because of that, the pairs inside yield much higher fingerprint similarities, whereas the pairs between inside and outside yield low similarities. And it turns out that distance or floor types actually does not affect perceptio because perceptio is robust against reduced signal amplitudes. And that is because we've actually zoomed out from the actual time series amplitude, and we've actually looked into the timing information, as I have explained earlier. We also found that the value of the signal decreases as we jack up the background noise quite a lot. And actually, it turns out that starting from about 85 dB, where even with human ears we cannot hear anything else but the background noise, then we started to see this happen. And also, we found out that the pairing time is proportional to the frequency of events. I'd like to focus on the first point, But the details of other points are also illustrated in the paper, and I encourage you to read our paper. So here I'd like to present our evaluation results on the event detection. And to do that, we present the receiver operating characteristics curve, or the ROC curve, which is a plotting true positive on the y-axis and the false positive on the x-axis for each sensor compared against the ground truth as we vary different amplitude threshold for signal detection. So we plot the ROC for a walking event or sets of walking events, and the area, the larger area under the curve means better detection accuracy, as most threshold yield a high true positive with relatively low false positive. And the green dotted line in the middle represent random guess, as that is the curve that depicts true positive equals to false positive. And the ROC on the left, the figure on the left, depicts the devices inside, while the right figure depicts the attacker's devices located outside. And each curve of each figures represents the different sensors. For example, on the left figure, we show the geophone, the microphone, and the motion detector ROC curves, and we omit power meter and accelerometer because they do not have the capability of perceiving a walking event. And the takeaway message is that all the devices inside, in other words, the figures on the left, have a high signal detection accuracy, yielding high area under the curve, while attacker devices outside, depicted on the right, yield low area under the curve that is very close to the random guess line. And with that, I'd like to conclude my talk. So Perceptio enables context-based pairing across devices that do not share any sensor types. And so we provide a more practical solution to context-based pairing. We also do not require tight time synchronization, nor any prior training phase. And also, we demonstrated a proof of concept implementation and a real-world comprehensive evaluation. With that, I'd like to end my talk. But before I end my talk, I want to announce that I'll be joining the National University of Singapore. So if you're interested in sensing or IoT security-related problems, I'd be happy to chat with you for potential collaborations. Thank you so much. And I'll be happy to take questions.
Okay, congratulations on your new position. Questions? Can you state your name and association?
Sure. Alex Gampman from Qualcomm. So in your experiment, how long does it take a pair of legitimate devices to establish, let's say, a 128-bit key that is secure against an external adversary?
So that's a great question. And actually, there's not one single answer that I can give you, because that depends on various parameters, specifically how frequent the events are. So if you have a single housing that is occupied by a single occupant, then obviously it'll take longer because you'll have less activities. But if you have more people, then it takes shorter.
Do you have an? Can you give us a range?
But rough idea is
like hours.
Right. So it's on the order of like hours to a day from our experiment. But I'd be happy to give you more information. We've actually performed a simulation on this, and it's in the paper as well. Yep.
Peter Neumann again. As someone who's played a lot of squash in his life, I was fascinated with your constructive use of the squash court. Recognizing that the Internet of Things forces you to think out of the box a little more, leads you to think that there is no box anymore. And I think you've done a nice job of cross-coupling things that are inherently looking like they're incompatible. But I'd like you to look at the longer future. Mm-hmm. You're doing essentially dynamic checking all the time here. Right. Can you have a hybrid model where you combine this with some way that also uses, say, public key crypto or something like that in the future, where standards have emerged and suddenly you have the possibility of having some standardization across all of the things that are going to be involved, and envision a combination of your approach with something that helps in the initialization process. I think there's a mammoth problem here when people start hooking everything in the world up to their Internet of Things in the house, how do you configure all of that stuff, and how do you do it? So can you conceive of something where actually you are using your approach in combination with other approaches such as cryptography?
Sure. So thank you for the question. So if I understand the question correctly, so you're asking how initialization of this protocol would be actually deployed in real world, and how do we standardize this? So actually, that's a great question, because we were envisioning that there would be like close to zero involvement of the human user, other than taking out the product and maybe pressing a button to start it, and we're all going to be working out of the place. So in order for this to happen, of course, the manufacturers, various manufacturers of the smart home devices have to converge to Perceptio protocol. But once that is done, actually it doesn't require any additional hardware implementation or addition to these devices, because we're basically just retrofitting the software on it. So that's one thing. And also the other thing is we would not require the vendors to pre-insert the keys or anything like that. So that would be one solution.
I apologize, but due to time limits, we have to take your questions offline. Okay, thank you.
Yeah, thank you.